So this question is about tic-tac-toe. And it's a question which, well, tic-tac-toe is a game that is pretty well known for always ending in a draw if you play perfectly. But this question isn't about playing perfect tic-tac-toe, it's about playing random tic-tac-toe. So for those who don't know the rules of this game already, it's a game played on a 3 by 3 grid of unit squares, and two players, one using X's and the other using O's, will take turns choosing an empty square in the grid and writing their symbol inside it. A player wins the game by being the first to create a horizontal, vertical, or diagonal line of grid squares that all contain their symbol. So for example, this wins, and so on. Given that both players in the game of tic-tac-toe play by randomly choosing squares to fill in, what is the probability that one of them wins the game? All right, so this is a difficult problem, partly because the end result for a winning game and for a drawn game look pretty different. So in the case of a drawn game, you have a bunch of X's and O's that don't really form any any three in a row of rows, columns, or diagonals. And notably, this will always be a completely filled grid where there are no more moves left and no one has won the game. But on the other side, a game that wins could end very soon. So for example, this game is already over and there are still 4 spaces left. Of course, you could also have more squares filled in and still have a winning game. So the difficulty is, how do we count the winning games and the drawn games in a way that makes these boards look similar as possible? And so my strategy that I want to show you is, let's just let the players keep playing, filling in the board completely, even if someone has already won the game before that. So this way, every possible game of tic-tac-toe will result in some configuration where the board is completely filled. And if, for example, we assign X's to the first player and we assign O's to the second player, the key point is that every game ends with 5 X's and 4 O's. So this is the way that we're going to do it. Even if someone has already won the game, we're just going to let them fill in the board completely. And so the reason that I do this is so that there is a difference between the way a drawn board and a winning board look. So whenever someone wins a game, we can be sure that the final board will contain some 3 in a row. So for example, if I just look at this board, I don't even need to know the order that they played these symbols. Just by looking at the fact that there is a 3 in a row in there somewhere, I know that at some point this game ended and someone won the game. And even in the case where something like this, like you might think, oh, but what happens if there are multiple 3 in a rows like this? Then what happens? And the answer to that is, we still know that someone has won the game. We just don't know who, but that doesn't really matter for this question. So the key point now is that with every board looking exactly like this with 5 X's and 4 O's, we just need to count the number of boards in which there is a 3 in a row of X's or O's somewhere. So how can we go about counting that? And the strategy that I want to propose is complementary counting, which is counting the opposite of what we're trying to find. So now let's count the number of boards that end in a draw. So we can imagine we have our 3 by 3 board, and I want to place, for example, I want to place some O's in a way that I will not have any X's or O's that end up in a 3 in a row. So this, for example, is one way that you can do it. But how do I count all of them? So one thing that you might notice first is that if you want to prevent any horizontal or vertical X's that are in a row, you need to place O's in one of these 4 configurations. And these are the only way that you can prevent a 3 in a row horizontally or vertically of X's. And keep in mind that this is not okay, because at this point we've already formed a 3 in a row. We want to avoid that. So here we have 4 possible ways to put our O's, where there are no horizontal or vertical X's. And importantly, we need to put the 4th O in one of these 3 spots right here. Because otherwise, the X's would form a diagonal there. So notice that in this first case, there are 3 possible configurations. We have this one here, we have this one here, and we have this one. Now notice that these other 3 configurations are just rotations of the original. So because of symmetry, each of these also have 3 different configurations. So in total, there are 3 times 4, or 12 ways that we can position the X's. So, well, sorry, that we can position the O's in such a way that there are no 3 in a rows of X's or O's. So that's not the final answer, of course. We need to find the probability that we end up at one of these grids. So how many possible grids could we have ended up with? And the answer to that is 9 choose 4, which is also equal to 9 choose 5, because there are 9 spots and there are 4 ways to put O's and there are 5 ways to put the X's. So this is the number of total boards that we could have ended up with. So this, if you calculate that, that's 210. So there are 210 possible final boards. 12 of those boards will result in a draw, which is 2/21. So the probability that you don't end up with a draw, therefore the probability that someone wins, is 1 minus 2/21, which is 19/21. And that is our final answer.
Hey, this is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.